Good morning, everyone. Once again, a very good morning to everyone for welcome you all for the second day of this faculty development program. And I think yesterday we were discussing about the basic components and the various architectures, and even we were discussing about the electric motors and the design related concerns actually of an electric motor. So today the discussion is going to be on the inverter systems, and even we'll be talking about the converters as well. When you look at the current electric vehicle market, right, especially in India, so this inverter system is playing a very significant role, which is imposing a lot of challenge because today there are many motor manufacturers in India who can manufacture an induction motor or a PMSM motor or a BLDC motor with a very small amount of import in it, but many of the manufacturers are still struggling to develop their own controller or the inverter module in order to control the motor. So it has become a very big challenge today in the market. There are few companies in India, which is indigenously developing the inverter system for electric motors for EV application. So I know that in my opinion there is a strong demand, there is a strong opportunity to do research and development in this particular area. And as a faculty member and research scholar, I would strongly recommend you people to concentrate in this particular area since there is a huge demand. So to make you people aware about a company, I think one of the well-known company in Kerala, known for this inverter and drives, is basically a company called C Electric Automotive Drives Private Limited. I don't know how many people have heard it. Yeah, it is based out in Cochin, in Kerala, and yes, so that team is really putting a lot of effort on for developing the inverter systems and converters for two-wheeler and three-wheeler applications. The reason is I yesterday mentioned clearly that two-wheelers and three-wheelers, they are the major market in India, Indian automotive market. So any product that is meeting the two-wheeler and three-wheeler sector, definitely it will get its a lot of benefit actually. So that's why. So today the discussion is going to be on the inverter system, and we will talk about how different companies have approached the inverter design. What are all the various components of an inverter system, and we will also talk. We will also see a case study on how a particular manufacturer has put efforts to develop inverter system for his or her electric, for its electric vehicle, right? So that's the discussion going to be today. So the first thing is, as I told, the same words apply here as well. Yesterday I told whatever the questions, kindly drop it in the chat box, and try to be as much as communicative, more in this session. I would like to engage all the participants during my session. So that's how I do generally all the sessions, and I request the same from you all participants. So whatever the questions, anything, feel free to drop it in the chat box. So when we look at the inverter, right, it is a very important component of electric and hybrid vehicle. So because it is going to, this is the component which is going to control and operate the electric motor. And basically everyone know inverter is just to convert the DC into AC DC from the battery source, and convert that into the AC input power for the motor drive. And similarly, basically these systems are basically bi-directional. You can see that even it also has a bi-directional DC-DC converter integrated into this particular inverter module. So there, if any at any point of time, if there is any regeneration, right, during the braking event, if there is any regeneration happening, then there will be a conversion from AC to DC back to the battery pack. So both the things happen in the same way, and this component plays a very important role. And let's understand this. So this is an example of an inverter module, how an inverter module look like, right? This is an example of an inverter module. You can see that we will discuss about that in more detail in the coming slides. So this is what an inverter module is like, and you can see that basically the inverter modules are placed very close to the electric motor, right? Yesterday, if you remember, I have shown you some picture where the inverter was sitting in top of the electric drive unit, the traction drive unit, right? So that's how we place the inverters in by even all manufacturers, most manufacturers, that's how they place it. And the reason for placing the inverter very close to the traction drive unit, any answers for that? What do you think is the reason for placing the inverter very close to the traction motor or the traction drive unit? Is there any thoughts on it? Why they do so? Okay, minimize losses. Okay. Wired inductance, very good. Yes. So if you remember yesterday, I told a typical electric car will have certain meters of, approximately certain meters of high voltage cable. Do you people remember that? How much meters did I mention? Approximately. Yes, yes. It is 35 meter, right? It is 35 meter. Appropriately 35 meter will be there in most of the electric cars in the market, right? So that is the amount of the length of the cable, high voltage cable. And as I mentioned, they use aluminum as the conductor, the conductor which is there in the instead of copper, right? So because of which they need to go for a more cross-sectional area compared to a copper cable. So already this the high voltage cable which they use in this electric vehicle domain, it is very costly, and all the companies, they try to reduce the amount of cable usage from one generation to another generation. If 2011 the company is developing one inverter, and 2015 if they are developing a new one, obviously they will try to reduce the cable usage, which is going to be a considerable amount of cost reduction factor, right? So if in this, for example, you can see that this inverter which is placed, it was placed in the previous model like this, and you can see the difference. And in the new model, the inverter is being placed at this position, which is very close to the traction drive unit compared to the previous model. And you can see the difference, right? The difference is mainly on the high voltage cable. So you can see that there are totally in this particular traction unit, there are two motors. So that's why there are two three-phase terminals, three-phase cables coming out from the inverter to the electric motor, and you can see the connection. And when we bring the inverter very close to the traction drive unit, what they have done is, instead of putting a cable, they have connected the terminal directly, right? And you can see that by using brackets, they have directly mounted the inverter on the traction drive unit. So compared to the previous model, the new model, the traction inverter comes very closer, and as you rightly mentioned, participants, the losses can be drastically reduced. And also, not only the losses, the overall the density, the volume that the inverter is going to occupy, or the volume that the drive unit, the combined drive unit is going to occupy, has been reduced. You can see the distance between the previous model, between the inverter and the traction unit. You can see the new model, so it has been drastically reduced. So the space, we get a lot of space remaining for placing any other components required, right? So that's the benefit that they can get. So generally, when you look at the inverter, right, the very important the property, or I would say parameter, when designing an inverter, that a design engineer takes into consideration is power density. So whenever a new inverter design project starts, they generally set the target for their power density, the target for their specific power, the power ratings and current ratings, and the overall current density that they can handle. So all these things are becoming a very important targets when a company or a manufacturer develops an inverter. So when you look at this particular example, when you look at this chart, we can very clearly see that Chevrolet Volt, it is a hybrid vehicle. Cadillac, another hybrid vehicle. Toyota Prius, it's a hybrid vehicle. Nissan Leaf, it's a pure electric vehicle, and i3, it's a pure electric vehicle. Audi A3 e-tron, it's a pure electric vehicle, and Model S, it's a pure electric vehicle. So we are seeing the inverter module for both the electric and hybrid vehicles, and you can see that power ratings of these inverters, which are ranging from 75 kilovolt ampere to 215 kilovolt ampere, and you can see the power density. So which company has power density, very high power density in this particular range, in this range of inverters? So it is actually Tesla Model S, right? So Tesla Model S, it is showing 30.1 kilovolt ampere per liter of volume. The power density is close to 30.1, and next to this position is Toyota Prius, which is having 23.7 kilovolt ampere per liter, right? So that is the power density of different the inverter designed by different manufacturers, and the specific power is also provided here. So we can understand that each and every, basically not all the inverters are designed in this. Basically, there are certain factors which decides the power density, and so each and every company applies different methodologies, right? Each and every manufacturer they apply different methodology to achieve a maximum power density. Some companies, yes, they meet it. Some companies, they literally struggle to meet that, right? So that's where the challenge is. And most of the time, it is believed that the manufacturers develop the inverter. It is not like that. Most of the companies, they don't in-house develop the inverters, right? Instead, there are some other tier 1, tier 2 suppliers who build these inverters for this manufacturer and supply to them. For example, there is a company called Hitachi Automotive, which develops inverters for the vehicle application. And so similarly, globally there are so many companies which work mainly on the inverter and motor control technology, right? So I'll give some examples when time to time during the session, right? So let us look at a small teardown of different companies' inverters. When you look at Chevrolet Volt, Nissan Leaf inverter, and Tesla Model S, right? Almost all the three inverters have the similar components. That is what we need to understand. All the inverters almost represent the same. They do the same function, and almost they have the same components. Sometimes from different suppliers. That's the main thing. But the overall design remains same for an automotive inverter. And even the standards, all these inverters follow the functional safety standards. And as per the SLD means Automotive Safety Integrity Level D, right? It is the level, it is a safety level which is to be followed by any electrical and electronic component manufacturer in automotive domain. So we call it as SLA, SLB, SLC, and SLD level. So depending upon the level A, B, C, D, it will be like very stringent. D means it is very stringent. They need to meet very stringent norms, testing regulations, right? Because this inverter component is a very important component, and there are many chances for short circuit, many chances for higher voltage and disturbance in the system, and higher inrush current possibilities are there, because there are so many power control, the capacitors, DC link capacitor, so many components are there which can lead to any sort of problems actually if it is not properly controlled. And that is definitely a cooling system placed in this inverters. So let us look at the components one by one. So most of the if you look at the inverters, the first one is the control board. So basically the control board functions to control the it has the control algorithm basically, and supports control of the motor as per the requirement. And the second one is the DC link capacitor. It's a very, very important component of an inverter or an automotive electric vehicle inverter. And everyone know, so DC link capacitor, anyone have you people used in your previous projects or anywhere? A DC link capacitor? Anyone? So here the purpose of this DC link capacitor, it is definitely playing a very important role. So because you know that we use the input DC source, DC voltage as the source, and we know that the batteries will be like ranging from 200 voltage to 400 voltage if it is a passenger car, and more than 400 800,000 voltage if it is a bus or a truck. So with such a huge voltage of power, coming up to the motor, right? If there is no DC link capacitor, right? If there is no DC link capacitor in this particular inverter, what will happen? What will happen? Any idea? Any idea? If there is no DC link capacitor in an electric vehicle inverter, what might happen to this inverter component, inverter system? Am I audible, ma'am, actually?
Yes, sir.
Yes, sir.
Yes. Is there any answers in the chat box, or so any idea on this? Okay. DC link voltage not be stable. Okay. Okay. Yes, definitely. Yeah, the stability nature will be a problem, but more than the stability, the serious issue will be the inrush current. So when such a high voltage and a higher current flows into the system because of this switching, and you know that this PWM operated systems, basically they behave non-linearly, right? And these systems they can definitely shoot up the overall inrush current, and it has been understood that when there is no DC link capacitor, the max inrush current can go up to 3000 ampere. 3000 ampere in a automotive electric vehicle inverter. So without a DC link capacitor, definitely it is going to be very tough to work with this high voltage electric vehicle systems. And the temperature rise and everything will be very dangerous, that it can damage the circuit very easily. So DC link capacitors are definitely unavoidable in the design of a inverter system, right? And similarly the DC link bus bar, so which is going to carry the huge amount of power during the starting time or discharging time. So I will explain about the different applications where they are applied. And the phase bus bars, we are the inverter is going to get connected with the motor, right? So if there is one motor, there are going to be three phase lines, three phase bus bars which are going to connect with the system, and there will be terminals coming out of these inverters. You can see the terminals here. So this is the IGBT module. You can see this IGBT power module mentioned here, and the gate driver circuit which will be sitting in top of the power module. And basically today, the previous inverter design, the control board was separately mounted and the gate drivers were separately there. But today, the recent inverter modules developed by Tesla Model 3, Model Y, and even in the Toyota Prius, the recent Toyota Prius, both the control board and the gate driver board for the IGBTs. So both these boards are connected together. All these efforts are why these efforts are taken to bring each and every component, to integrate each and every component. Why it is done so? Why they need to bring the control board and integrate that with the gate driver circuit? Why they need to bring all the components close together? What is the sole purpose? Any answer? One of the main purpose is to improve the power density of the design. right? The overall power density of the design. So they want to shrink the overall components and overall power density. And when power density is improved, they can what they can do is the manufacturers can reduce the size of the internal components. So if we improve the power density of the system, then I can reduce the size of the DC link capacitor. I can reduce the size of the inductors that I'm using there. So each and every component can be downsized and we can optimize it further to improve the performance and cost as well. So that is the main reason people improve the power density, and power density is the very important factor that is actually determining the success of a inverter in a system. And finally, we can see that there is a serpentine model heat sink which is connected below the IGBT. So which is nothing but to cool down the IGBT and maintain its temperature in an optimal range. So when you look at any inverter, any electric vehicle inverter, a similar thing is applicable. The same type of structure is applicable, but depending upon the company's technology, the IGBT modules, it can be splitted. It can be splitted into multiple IGBT modules depending upon, we call it as interleaved, right? So the interleaved design is recently applied in almost all automotive inverters. We will talk about that, the interleaved design. So when we look at the inverter integration, into the electric vehicle drive system, different companies try different methods. A radial housing mount, this is actually one of the way inverters can be mounted on the electric drive system with the motor. And this is another type of mounting, radial stator mount. Around the stator itself, in around this kind of shape, the inverter can be designed. And the third one is axial end plate mount, which will look like this, and axial stator mount, which will look like this. So different companies approach the inverter position, inverter integration differently. So the picture which we saw earlier, the Toyota Prius, which inverter mount they have selected? Which inverter integration have they selected? Do you remember this picture? So now, can you people tell me which integration method they have selected? So in Toyota Prius, it is the radial housing mount, right? So they have placed the inverter radially, and one of the main reason they have done this is to have better thermal isolation between the inverter and motor. So in a case where if the motor is developing a lot of heat, then the temperature rise is there, then definitely placing the inverter very close to the motor will not be a good idea. So definitely that will actually create problems to the inverter operation, and even many other cases also they take this decision. For example, when there is more amount of electromagnetic radiation created from the motor housing or the motor system, then definitely placing the inverter very close to the electric motor may not be the right idea. Or if there is no other way that the company has to integrate the inverter into the drive system, into the motor unit or the drive unit, then obviously they need to make necessary changes or necessary improvements in the EMI, EMC or temperature rise. All these factors they need to consider, right? The only challenge in this kind of situation is achieving the power density target. It's very difficult for them, and obviously they need to have a separate cooling system for the the inverter and the electric motor. Whereas in Tesla Model S, if you people remember, let me take the example. So Tesla Model S drive unit, if we say, so in the Tesla Model S drive unit, let me just show the picture. So we can see that in the Tesla Model drive unit, it is very clear. You can see the motor, and it's like on the end plate itself, they have the inverter sitting there, the Tesla Model 3. and you can see that it is having a common cooling loop. The cooling loop is actually common for both these components, and that's the difference. When we have a motor and inverter in a common casing or a common loop, it becomes very easy for the cooling system to operate. And only thing is, as I mentioned, they have to consider other factors like the temperature rise, or they need to consider the EMI EMC issues, related issues, and their design requirement, design challenges. Some companies, they are still struggling to integrate the inverter inside a particular transmission or the whole e-drive unit, right? So different companies are taking different approach on the inverter design, right? So let us take this particular case study done by Toyota Prius. And as I mentioned, this is the Toyota Prius inverter, which is placed on the e-drive unit. And when we tear down this particular this power control unit of Toyota Prius, these are the different components, how they have integrated it. Let us see. First one is the control circuit board, and this is the casing. This is the aluminum casing, which is going to be the component where the control boards and all these components are going to be. This is basically a platform, right? This is basically a base platform for mounting all these components. And you can see the DC link capacitor, the bigger one, DC link capacitor, and the power module, IGBT power module. And we have a reactor, and we have a current sensor module, and the DC-DC converter control module. So this is not just in Toyota Prius. They have not just made an inverter. They have integrated both inverter and DC-DC converter into a single casing. This is how the trend is going on today. So instead of having a separate box for inverter and separate box for DC-DC converter, all these companies are trying to integrate these components, right? So these are the various components present in a electric vehicle inverter system for either it is electric or hybrid vehicle. So the key modifications that were taken by that were present by Toyota in this particular inverter are: change the signal line input to the board to terminal connection. So they have optimized the terminal connection, the three-phase terminal connection of the inverter from the IGBT to the control board, the gate driver board, and similarly from the gate driver board to the that means from that output terminal to the motor terminal. They have optimized that line, optimizing the component placement by integrating the capacitors and terminal block. So they have, compared to the previous model, they have modified the capacitors a little bit in terms of its bus bar and its dimension. The capacitance value has been changed, improved, and we will discuss about that in the coming slides. And also in this particular newly developed Toyota inverter, they have adopted a double-sided cooling structure and a separate RC IGBT instead of a conventional IGBT. They have implemented the reverse conducting IGBT, which we will discuss about it. And reduction of smoothing capacity by adopting new microcomputer and speeding up the boost control. So in addition to adopting different IGBT technology, they have also tried to reduce or optimize the DC link smoothing capacitor by making certain changes in the microcontrollers, right? Let us understand what is their improvement. First thing is, let us understand the specifications as usual. So when you look at the previous model of this inverter, the Toyota Prius inverter, these are the previous model specifications. We can clearly see the boost voltage of the previous model is 520 volt, and the system maximum output was 73 kilowatt, and the motor maximum output was 45 kilowatt. The maximum motor rotational speed of that model inverter was 13,500 RPM. This was the specifications of the previous model of Toyota Prius, right? And you can clearly see the weight of the whole the inverter system was 11.9 kilogram, and the volume it occupied was 9.4 liters, and the output density was 21.5 kilovolt ampere per liter. The max current it was able to handle was 135 ampere, right? So these are the specifications of the previous model, and kindly look at the specifications of the new model. What are the improvements they have done in the new model from the previous model? The first one is boost voltage. So the previous model had 520 volt. That was the maximum boost voltage they can go. And the new model, they have achieved 580 volt. So now the question is, what is the significance of achieving higher boost voltage from a inverter system? As I told you, that there is a DC-DC converter basically present in this electric inverter, EV inverter. What is the purpose of this DC-DC converter? And I told it is a bidirectional DC-DC converter. So what is the sole purpose that do you people think? What is the sole purpose of this DC-DC converter in this particular Toyota Prius application? Any idea, any opinion, any view? What is the sole purpose of using this DC-DC converter in this EV application? Any idea?
Regenerative braking.
Okay. Yes, yes. That's the reason it is a bidirectional DC-DC converter. Yeah, but the sole purpose for any component, there will be a very important function. So yes. So to increase the DC link voltage, one of the main reason of using a DC-DC converter in EV hybrid vehicle, especially because see, electric vehicle is different, hybrid vehicle is different. Electric vehicles will generally have a bigger battery. Bigger battery, that means higher voltage will already be there. But if it is a hybrid vehicle will have a smaller battery in the sense compared to a electric. If an electric vehicle is having a 400 volt, 500 volt battery, and a hybrid vehicle will have close to 150 voltage battery, 150 volt DC battery. So basically, when we are accelerating an hybrid vehicle, right? Initially, it will be operating in the electric mode, or it can work in a combined mode as well. So during the initial acceleration and timing, we can't accelerate the electric vehicle with just that 150 volt, which is not sufficient to generate that maximum acceleration. So obviously, the hybrid vehicle will need a boosted voltage for a minimum amount of time in order to have a better acceleration. So the DC-DC converter basically helps to boost the voltage from 150 volt DC from the battery to close to 400, 500 volt DC to the inverter side. Right, and similarly during the operation, during the regenerative braking, it does the bidirectional. It also do the buck function as well. Right, that is the purpose of this DC-DC converter. At the same time, when we look at this DC-DC converter, as I mentioned, so in this case they are boosting it from 520 volt to 580 volt. It is nothing but to improve. So when I'm saying that compared to the previous model, the new model has higher boost voltage, it means the new model can accelerate faster. Right? It means the new model can respond quicker compared to the previous model. So the voltage, it is nothing but it is directly proportional to the amount of acceleration behavior of the electric or hybrid vehicle. Right? And similarly, not only the boost voltages has been improved. Look at the motor max current specification. So the previous model, the motor max current was 135 ampere RMS current, and you can see the new model, it is improved to 164 ampere RMS, right? And look at the specification of the weight. Look at the weight. It is 11.9 kilogram to 10.2 kilogram. And the volume has been reduced from 9.4 liter to 6.3 liter. What is it called? What is this called? Weight has been reduced, volume has been reduced, but current has been improved, voltage has been improved, overall output has been improved. So what is this called then? It is called the power density, high power density, high current density, right? So here in this case, compared to the previous model, Toyota Prius was able to achieve a very high power density and current density because of making the following changes. Right, the first change that they have done is the power stack. So compared to the previous model, they were using a conventional IGBT design, whereas if you look at the power stack of this, the Toyota Prius, they have the power cards, the cooler. This is the cooling loop where the IGBTs will be placed inside, and the insulating plates, thermal conductive grease, compression plate spring, and spacers. So all these components make IGBT power stack. And basically a power card, when we take a power card, it is the resin molded package including the RC IGBT, reverse conducting IGBT, and the freewheeling diode. So in this new design, in the IGBT design, they have integrated both the IGBT and the freewheeling diode. So both are integrated together, and we have the heat sink and terminals coming out very optimally, compared to the previous model. So basically here they have tried to enhance the thermal performance of the IGBTs, and we can see this from this picture, the 2-in-1 structure. Basically they have adopted a 2-in-1 structure which allows the power card to be securely mounted. And this is basically a modular design. Say today Toyota Prius, yes, they are making for example 70, how much was the power of the vehicle? It was like the motor power was 85 kilowatt. So yesterday previous model 73 kilowatt they were making, and the new model 85. In future they might go for 100 kilowatt model, right? So for every new generation, they don't need to completely redesign the IGBT structure. What they can do is, earlier they were doing so. Earlier for every new generator they have to redesign the IGBT structure and all these things. But now what Toyota Motors has done is they have created a modular design, and this modular design allows the number of power card modules installed to be improved, to be increased or decreased depending upon the vehicle application. If they are going for a small car, they will obviously need lesser power, and they will reduce the overall power card module typically. And if they are going for a bigger vehicle, for a higher output vehicle, they will increase the number of power card to allow higher output current carrying capability. So end of the day, this new 2-in-1 structure has improved the Toyota's flexibility for the market. If there is a new model they want to launch in the market, they will be very competitive. They can very quickly launch the model because they can develop the inverter very quickly compared to the other manufacturer. This is one way of improving the design efficiency of an inverter system. And basically the reduce in this particular case, reduce of 22% of the physical size was possible, and nearly 55% of the inductance between the P and N terminal was eliminated and was achieved by eliminating a wire between the upper and lower arm of this IGBT module. So basically a 2-in-1 structure has been implemented here. And as I mentioned, they have implemented the reverse conducting IGBT design in this particular inverter module. We can see the different components, the freewheeling diode, the IGBT card, and you can see the terminals, the separate terminals. And this is basically the RC IGBT. So it integrates the IGBT and the freewheeling diode. And overall, the device, the occupied device area, right, that has been drastically reduced compared to the previous model, and obviously it has led to the improvement in the power density. So compared to the previous model of Toyota Prius inverter, the new model has achieved. This is all possible. These specifications we saw that, right? The 135 ampere to 164 ampere. And overall power density, the output density improvement, 21.5 kilovolt ampere per liter to 41, nearly twice, almost twice improvement of the output density, right? It is all possible because of these modifications on the IGBT, and this reduced the overall element area by 32%. And only the power, once we bring down, once we integrate too much, one of the major challenges, deterioration of the losses due to the reduction in the element area. So what will be the issue is, we might see there will be a temperature rise, a high temperature rise in this IGBT, because the surface area which is available for cooling has been reduced, right? So now what happens is, now the challenge is towards cooling down, or the bringing the IGBT for a optimal structure. That is the another challenge that they are meeting, and they have handled this challenge with other way. We will talk about that. So and they also, Toyota also, they have also implemented something called super body layer structure. We call it as SBL structure in this new IGBT, which they have selected for the inverter. And this new SBL structure, basically helps us to accumulate more hole carriers from the collector side and stimulate the infusion of the electron carriers from the device surface. So that is the main advantage that they can get from this new IGBT that they have developed, the 4th generation IGBT. So during the switching on time, lowering the on resistance of the device, and during the switching off time, discharge the high concentration of accumulated carriers quickly. That is possible with this new IGBT design, right? And overall, they have reduced the substrate thickness by 24%. So in one way, they have reduced the element area, and the overall element usage has been reduced, and output density of the element improved by 80%, and high output density is also achieved in this case. And overall, the device losses, the associated losses, switching losses of this new IGBT compared to the old IGBT, nearly 45% improvement has been achieved. Right. So now it is not only because of going for this RC IGBT design and the integration, it is also by implementing a better cooling system, for this IGBT. So in this new IGBT designed by Toyota Prius, what they have done is they have implemented the double-sided cooling structure. So in the previous generation, if you look at, this is the IGBT module, and you can see the cooling plate, it was a single-sided cooling loop which was used in the previous model, and they were using wiring bonding, the wire bonding as the methodology. And today, it has become a trend, it has become a trend to avoid the wire bonding methodology, and instead of that, there are many other ways that the companies are trying to do. So for example, in this case, you can look at, this is a new IGBT module which has been developed by Toyota Prius, and you can see that the new IGBT module, it is a double-sided cooling structure. Compared to the previous model, it is a double-sided cooling structure, and it is having more effective heat transfer possibilities compared to the previous one. You can see the IGBT module, which is also has supported with an aluminum silicon electrode on top of it, with a nickel electrode. All these, everyone knows nickel, basically it is a high temperature withstanding capability material, and in addition to that, they have a solder between the heat sink and the nickel electrode, and here also another insulation plate, and the we have the cooling loop. So we have the double-sided cooling structure. So the heat radiation happens in the both the side of the IGBT. So which becomes an added advantage and for this system. And even though the element area and overall integration has been done too much, it was compensated with a double-sided cooling structure, right? And if you look at the present trend, the today's trend. If you look at this, but in this case, the coolant will be running inside this. It will be running inside this cooling plate only, right? But the new trend, the new latest trend, it is going to be adopted by Tesla, right? It is going to be immersed in IGBTs. Instead of putting a heat sink and cooling down the IGBT, in coming days, there will be a immersing coolant. There will be a coolant into which the IGBT will be directly immersed. At the same time, the IGBT will not have any issue. And what is the coolant? Any idea? Any idea what is the coolant technology will be? Will it be water or will it be ethylene glycol? Because these are the general cooling agents which are used in IGBT heat sinks. But the latest one for the inverter, it is polymer. It is polymer. It is nothing but perfluoroethylene. It is a polymer, basically, that too especially a liquid polymer. It is a liquid polymer into which the IGBTs can be immersed. So that is the current new latest trend, and the silicon nitride IGBTs, silicon carbide IGBTs, even the gallium nitride IGBTs, MOSFETs, all these components can support this new cooling methodology. But at this point of time, the cooling methodology adopted by the companies is this kind of cooling plate heat sink based cooling structure only. But in future, definitely, as this polymer is becoming very applicable for many applications. We will see very soon that the polymers will become the main heat sink cooling system. And when we have a immersion cooling system, then in that case the IGBTs can be further downsized, the MOSFETs can be further downsized, and further power density is possible. Higher power densities are possible. That is the improvements that can be done in this IGBT. So this is one start. This is one part of the improvement done by Toyota for their application. Right. The other way, the other optimization that Toyota has taken into consideration is nothing but downsizing of the capacitors. So the downsizing of the DC link capacitor, which is used there in their particular vehicle. So as I mentioned, DC link capacitors, they play a very significant role in the electric and hybrid vehicle inverters. And basically what they have done in this particular new design, what they have modified is the bus bar, right? So overall, we can see that placing the PN bus bar close to each other in parallel. So this is the previous model of the DC link capacitor, and this is the new model of the DC link capacitor. They have modified the bus bar design, and it has like improvement of the semiconductor switch control also possible. That means the control part of the capacitor, the control part of this DC link capacitor has been improved a lot. And by the improvement, what they were able to achieve is, compared to the previous model, they were able to reduce the capacitance that was required to operate. So compared to the previous model DC link capacitor, the new model DC link capacitor required a lower capacitance compared to the previous one, right? And what else on the structural side, what else they have applied? They have applied a newly developed thin film. What is the technology they use in this capacitor is nothing but the polymer film technology. It's a polymer film technology compared to the previous, the previous generation automotive inverter. They were using aluminum electrolyte based capacitors, but now for the past few years they were using the polymer film based capacitors, and they were very effective. And compared to the conventional aluminum electrolyte based capacitor, these new capacitors can handle more amount of inrush current. They can work at extreme conditions even with lower capacitance values within them. So that is the benefit they are providing. And you can see that the improved capacitor module not only reduced the mass and volume by 36%, but also reduced the capacitance by 41%. And also the overall equivalent series inductance was also reduced by 46%, which has improved the overall performance of the DC link capacitor. So it has also reduced the cost of the system, right? Because when the capacitance value reduces and all these things, automatically it will bring down the cost. And the volume and volume reduction obviously leads to higher power density. So compared to the previous model DC link capacitor, the new model DC link capacitor, which adopted the new thin films and the new modifications on the bus bar design, all these things lead to the improved DC link capacitor, right? So these are all the ways, different ways that the companies adopt, different methods the companies adopt to improve the performance or the overall performance of the system. And you can see this motor generator ECU calculates and IGBT control command from various sensor inputs. So basically what they have done is they have integrated the motor control board and the power control mode, the power module board. Both, that means the gate driver board as well as the control board, both were connected together, integrated together, right? So that is also a new optimization they have done in this new inverter. And we can look at this current sensor. The new current sensor, reactor current sensor, has increased the boost control cycle 10 times. In this the new inverter developed by Toyota, what they have done is they have applied new current sensors at different positions. See, this is the inverter circuit. This is the inverter circuit for the MG unit, the motor generator unit, and this is the current sensor for the DC-DC converter unit. The DC-DC converter unit. You can see this multiple current sensors, the various sensing points has improved the overall operational flexibility of operational accuracy of the controller, right? And because earlier they were not able to do so, what is the major challenge that do you think of placing the current sensor inside such a circuit? What do you people think, participants? What do you people think is the major challenge of placing a current sensor near a circuit like this? Any idea? What do you think is the major thing to be considered? Any input on this? What about the accuracy? Whenever we have a current sensor, the current sensor is nothing but it is going to provide the input signals from the currents to the controller. So the accuracy of this current sensor is very important. And when we place the current sensor in such a circuit, where the switching devices are placed, there are many chances that the current sensors may not give the right amount of right information, basically, right? So the new current sensors, the new latest current sensors, they have been improved in terms of physical ability and the structural ability. They have been improved to withstand any sort of electromagnetic radiation or any sort of vibrations. They are able to withstand now. So because of that, they were the recent current sensor, they are able to more accurately provide information about the current signals to the control board compared to the previous models. So that has enhanced, that has enabled the PCU, that has enabled the PCU to reduce the variation of the system high voltage. Basically it has avoided the if the control inputs are properly correct for the system, obviously there will be no unwanted variation in the voltage signals, right? So these current sensors play a very significant role in maintaining that system. So with reduce the variability of the high voltage, the capacitance of the inverter capacitor can be further reduced. That's true, right? So if there is a lot of variation, up and down variation is too much, right? And if that variation is keep on happening, then obviously the capacitance value should be for the safety perspective, we should be placing that in a higher end, right? But if we know that the voltage is properly managed in this particular new model, then obviously yes, the capacitance value can be further reduced for the capacitor, and it will obviously reduce the cost, size, volume of the whole capacitor, right? It's all benefit to the system, right? In addition to the DC-DC converter and the inverter level modifications, the Toyota Prius also modified the reactor design, right? You can look at the reactor. Reactor is nothing but the inductor. It is basically the inductor which is part of this DC-DC converter, which is going to be the one which is going to boost the voltage, actually, right? So this inductor, the reactor, has been optimized further in this newly developed inverter. You can look at the different modifications they have done. One is, what is basically the demanded characteristic of a reactor? One of the main characteristic is the stability of the inductance throughout the usual operating area, right? So the inductor reactor should showcase a very good stability throughout its operational area, and at the same time it should not occupy too much of space, too much of volume, and it should not weigh too much, right? So the reduction in the mass, reduction in the volume of a reactor inside an inverter is very significant. And once we reduce the size of the reactor, obviously it can lead to very high power density, right? So but what are the changes they have made? This is the previous model reactor that they have used. You can look at let me zoom it. You can look at the different reactor components present here, and this is the newly developed reactor by Toyota Prius. You can look at the new one. The quantity of the gap of the ferrous core, it has been modified, so better response to large current. Speed of the boost converter control is possible, right? So better response to the larger current was possible because of this new optimized core design, and the unified molded structure is adopted for the improvement of the vibration durability. So you can see that compared to the previous model, it has been become a molded structure, actually. So this has become a molded structure, and because of this, you can see the U core as well, the complete molded structure, because of which it is now able to withstand vibrations. You know that if the inverter is operating and at high frequencies, right, and the motor, basically it is integrated with the motor, right? So these inverters are placed with the motor. So when the motor is operating at certain different RPMs, right, there will be different sort of vibrations, and basically that can affect the reactor as well, reactor core performance. So this is in this newly molded structure which is developed by Toyota. This, because of this molded structure, this new inductors are able to provide a very high vibration durability, and the new reactor use a heat transfer sheet instead of silicon resin potting to limit overheating. So that is also one more included aspect in this particular system. So they have implemented compared to the conventional silicon resin, which is applied on the system, they have used the heat transfer sheet, and overall heat thermal performance was also been reduced, and compared to the previous inductor design, 27% reduction in the number of parts of the reactor was possible due to the added current sensor, and at the same time they were able to achieve the direct current superimposition characteristics that are actually required over a wide current range. And what they optimized is mainly the cross-sectional area of iron, or the number of coil turns in this particular core. That is very important, the change they have done on the coil. So this has overall improved 27% reduction in the number of parts. So the inductance of you can see this, the inductance of the reactance versus current rating of this reactor. And so depending upon the class of the vehicle, whether it is a compact class high voltage vehicle, or it is a mid class or a plug-in hybrid vehicle, depending upon that, the current rating requirement for the reactor will differ. So you can look at the close look. This is the close look of the reactor. So overall, the highly thermal conductive heat dissipating filler was applied. It enables a cooling structure that compresses the cooling sheets. So it has been applied in the newly developed reactor, and overall heat resistance and improved cooling performance was achieved. And overall, the new reactor is assembled using completely fastened tuck structure. And overall, it has in terms of manufacturability also, and not only in terms of performance, it is very thermal friendly, but it also, in a manufacturing perspective, assembling this inductor is was also considered, and they have made sure that the assembling of this inverter, the reactor, is to be very easier for the assembly line as well, right? So overall, by doing all these modifications, so these are all the optimizations they have done on the inverter side for improving the performance overall. And by doing so, what is they have achieved? From the first generation in 2011, they were having a model, and from 2011 to 2019, the latest model Toyota Prius, the inverter power losses has been drastically reduced, and at the same time, the breakdown voltage carrying capability was improved from every generation to generation, right? So nearly, you can see that nearly 28% reduction in the size, and nearly 19.8% reduction in the power losses, and nearly 14.2% improvement in the breakdown voltage. All these things are improvement made for the fourth generation newly developed Toyota inverter compared to the previous generation of third generation, right? So likewise, all these whatever the optimizations, as I mentioned earlier, all these, each and every optimization leads to the overall improvement, right? It is nothing but, it is not like one optimization brings a big change in the inverter. No, it's not like that. Each and every optimization, small optimizations on the capacitor, on the DC link capacitor, or the reactor, or on the IGBT, or on the cooling loop, all these things, all the optimization at each and every part, each and every part of the inverter brings us a very effective inverter design for the electric and hybrid vehicle application. So is there any questions from the participants till now, till this particular case study? We have a short discussion further, but before that, if any questions till now?
No, sir. No.
Was it clear when what I mentioned in this slide?
Sir, what about the switching frequency they are using?
Yes, the switching frequencies vary from what is a different models are actually model to model. Let me take one. Yeah, that's a good question actually. It will be better if I show the one of the example spec sheet itself, so that it will be definitely useful. Let me take an example. IGBT itself. So let me take the specification actually. I have the specification sheet for the same. Let me
It's okay, sir. The thing is that we need to know what is the range of switching frequency they are operating. That is the concern.
Yes, sir. So for example, if it is ranging from like if, depending upon the available specifications, sir. For example, from two-wheeler, as I mentioned, from the two-wheeler perspective or a two and three-wheeler application, the power ratings will be like very close to which will be operating at just below 10 kilowatt. In such a kind of applications, the IGBT, mostly the MOSFETs are preferred, compared to IGBTs. So these the switching frequencies will range from like to 1.5, overall 1.5 kilohertz, and from even from in terms of 2.2 and 2 to 12 megahertz of frequencies are possible in kind of operations at higher switching frequencies are possible actually.
Is it kilohertz or megahertz? What do you mean?
What, sir?
Is it kilohertz or megahertz you are talking?
Hello.
Am I audible?
Yes, sir. Can you hear me?
Yeah. I'm asking, is it in terms of kilohertz you are taking?
Yes, sir.
1.2 to 2.5 kilohertz.
Yes.
So what about the other Toyota price and all the machine which is having more than 100 kilowatt power? I mean, around 100 kilowatt range.
Hello.
Sir, am I audible? Hello.
You are asking for which thing, sir?
The high power motors, high power motor drives, especially for cars and all.
That means passenger cars and the applications, right? You're
Yeah,
asking
where
for
the motor rating is very high. That means the current is in the order of hundreds of amperes.
one moment, sir. One moment. Let me take this example. It's one of the best manufacturer for this IGBTs. MOSFETs are basically volt speed. So this is one of the famous manufacturer in worldwide right now. So let me take an example from them itself, so that actually I was looking for that spec only. So let me take this.
Sir, the MOSFETs can go very high switching frequency.
No, for this application, sir, actually, what I am talking about is actually for the EV application. So not on the general, the general perspective, general applications actually, right? So on the EV perspective, so when we look at this, on the EV perspective, that obviously the changes, there will be a lot of changes on the differences on their switching frequencies basically. So let me take this example. Wait a moment.
So why I have asked this, because you are talking about the inductor sizing and all, so that will greatly depend on the switching frequency.
Yes, sir, obviously, yes. Yes, sir. So this is an example actually. So So is it visible for you, sir? Actually, the specification.
Yes, yes, yes.
Yes. So this is a similar. Mostly, if you look at the the IGB MOSFETs which are applied for the EV application, mostly it's like from the onboard charger or the DC-DC converter or the inverter application. All these things, they are generally operating at almost similar frequencies actually. So one is, for example, the if you take the example of this particular model, what they have used in onboard charger application, they generally consider it as like 1 megahertz of application. Up to certain these kind of frequencies, they can operate at higher voltage, especially as the voltage goes higher and higher. The challenge of meeting this, meeting this particular application, challenge in meeting the overall temperature rise and selecting certain appropriate IGBT becomes a very challenging thing. And you can see the switching frequency mentioned here. It is like in this case, let me just. It is ranging from like 1 megahertz, and depending upon the application, yes, it can travel for even this one. This is the one of the widely used IGBT module. What you are seeing in front of the screen. This is from Infineon CoolSiC, we call it as. This is the MOSFET module. CoolSiC. This is based on the silicon carbide based technology, which is mostly implemented with the EV applications actually today in the market, either for inverter application or for onboard charger, DC-DC converter. All these different applications it is possible. So,
Sir, I don't think that the switching frequency will not go that much high for drive applications, especially at high power.
let me take it, sir.
Anyway, it's okay, sir. It's okay, no problem.
Yes,
No,
yes,
I
yes.
was just out of curiosity. What could be the switching frequency at this kind of high power application? That is what I am worried.
Yes,
So
yes,
when
yes.
we design some inverter kind of thing, which is
So
having
you are basically. Let me show the PPT. Now you are basically asking for this particular part, sir, like the IGBT, which is sitting there in this
correct,
motor drive circuit.
correct.
Okay. So it's not basically for the when you look at the fast charges, right? The higher rating fast charges, which I mentioned, maybe for those kind of applications, it will be definitely higher, sir. And for these kind of applications, basically, you will have a range of close to like 85 kilohertz to I've seen IGBTs, MOSFETs close to 100 kilohertz as well, 110 kilohertz, close to that area, especially for
Is it
the.
in drive? Is it in drive? That
Yeah,
means.
for the drive, for the electric inverter, the whatever I'm showing here, for the inverter drive application.
But I
Yes,
don't think that then there will be the switching loss will be drastically high because you are going to chop the current of say 100 more than hundreds of
yes,
amperes.
100. Yes, sir, yes.
So that the switching loss, what could be the expected switching loss if it is switching at say 100 kilohertz and all?
No, but overall, what they've done is like, sir, the overall improvement has been done. Optimization has been done at various stages actually. That's why they have overall losses. They were trying, taking different measures to reduce the overall losses actually. So that's where they have applied these different MOSFET modules, and it's not generic. What I mentioned, the switching frequency is very generic, and obviously, if such as switching frequency is used, obviously they will be applying different methodology to reduce the losses. Actually, it is not only on the on the IGBT MOSFET side, but on the control side also, they further improve the controller efficiency, the controller's operating efficiency, and they implement a faster control modules, microcontrollers, to further reduce the switching losses basically. So that is one way they are actually avoiding it. And moreover, the DC link capacitor, the DC link capacitor they are bringing up here, if they have optimized the DC link capacitor in order to even it can also reduce the overall losses actually associated with this switching frequencies. So they do,
Correct,
they do optimize these losses by using the optimization of each and every dependent components.
correct.
Yes, sir.
Okay.
Yes, sir. Yes.
Sir. Thank you.
So is there any other questions that we need to look at? So maybe I will show you a short, a video of. So an example how an inverter system and e-drive system has been integrated. So this is an example. Let us just look at this example. So that is one example actually of an e-drive system. So this is also one more example. You can see the e-drive motor. So this is what the bus bar that we were talking about, right? The three terminals, and this is the motor terminal with which it is getting connected. So this is the inverter module of this Audi e-tron vehicle. So we can clearly see that the cooling loop here, it was actually common for both this, the inverter and the motor module. So that's the typical, actually, the typical models, available in the market. Most of the e-drive system will be looking like that. So let me take a sample. So yes. So as sir mentioned, it was perfect to go without a proper answer. Sir, actually, I don't know who asked this question, but let me show this clarity, in this particular picture, actually, from STM. So you can look at this variation, sir. Is my slide visible, actually, what I'm showing, the PPT, the PDF?
Yes, yes.
Yes, sir. So you can clearly see, from the trend right now, it is going towards silicon carbide, and now it is shifting towards gallium nitride. And even already models like some of the models in Tesla, they are already testing it for gallium nitride, the same models. So very soon we will see that is being even applied in the real-time vehicle model. And you can see that whatever the frequency, switching frequencies, basically depends upon what is the different technology being applied, and there has been a drastic improvement on the technology related, especially on the silicon carbide and the gallium nitride side. And you can see basically it ranges from the gallium nitrides. Yes, definitely they can operate more than 80 kilohertz, and that's where I told that 100 kilohertz operations are possible in this particular range. Actually, even more than beyond that is also being tested. Beyond that also it's been tested for different applications already, and especially whatever the module which I'm showing from STM here, it's all applicable for EV application. And you can very clearly see the examples they have given for that. The high power DC-DC converters and charging stations, main traction inverters, onboard chargers. So all these components are, these are applicable for all these components. Even this gallium nitride transistor that they have developed newly, these also apply for the various applications, DC-DC converters, right? Even the photovoltaic related inverters, onboard chargers, and the upcoming autonomous vehicle related LiDAR technologies. All these things, these new models are applicable, sir, actually.
Okay, okay.
Yes, sir. So I think this video also gave a good understanding on how e-drive will actually look like, right? I think I will try to share that video to all the participants. Maybe if I receive a list of email and all these details, right? So is there any questions? Further questions are there related to this topic? So since this is very, just a small part of time available for each and every part of discussion, we can definitely discuss in detail. So I have given my email ID yesterday. So feel free to reach to that email ID by any time. So is there any further question on this particular thing?
Sir, one suggestion is there.
Yes, tell me, sir.
Sir, from your experience, at the end of every session, it could be it will be beneficial if you are suggesting some of the potential areas where the researchers can contribute something. Like
Okay.
what can be the drawback, or what is the present day problem facing by the industries, for some points where the
Okay.
people can take up some interested people can take up some work on
Yes.
that.
Yes. Yes. Yes.
You
Even. Yes, sir.
yeah.
Even this whole session, sir, whatever we have seen, whatever I'm explaining on what the companies are doing, right? So from where we can, one of the major problem that the companies are facing is the power density target, basically. So whatever the way the power density, the output density of the system can be improved. That is where the scope is right now in the market, right? And it is not just a research as a research scope. Today, if you look at IIT Madras, especially in IIT Madras, they have a complete team funded by Ashok Leyland, and they are currently working completely on the battery pack side, battery sizing, battery optimization, improvement, and all these factors. Similarly, for the inverter side as well, there are manufacturers coming from DC-DC converter domain or the inverter domain. They are ready to work with the institutions, basically in the area of improving the power density. So some of the methodology, one other thing is we can take some, I would suggest the faculties basically to do real-time testing. That is where first we need to concentrate on. So real-time testing has to be done, real-time data has to be understood, rather than just reading spec sheets from online or on other modes. I would suggest to do live testing with these components using the HIL SIL setup. And even though making a HIL SIL setup in an institute is quite difficult, but at least it is definitely possible to associate with some small companies. Example, I told C Electric Automotive Drives, which is in Kochi. So that company is basically a startup company, and they are definitely they don't have all resources. Definitely, they might not have all resources. So definitely, they might need support from faculties who will be eagerly interested to work on improving the power density design, improving the EMI. Especially one of the other issue is the EMI characteristic. So if you can develop a methodology to reduce the improve the EMI performance, EMI ability of the controller, and with respect to the vehicle environment or the other component environment, then these companies can further improve the power density and bring each and every component very closer together. Right, so that is where these companies are struggling. So instead of just working as a research project, I would suggest to work with these kind of companies, so that you will get the real-time data with you, and that will be more interesting rather than just taking doing something and publishing research paper. I would suggest more to closely working with these companies, sir, actually. So the different, as you mentioned, yes, definitely whatever the companies are applying, the companies optimization methods they are applying, this is where the scope is actually. That's how the faculty should take this particular session. So I'm telling that the DC capacitor, this particular DC link capacitor, this is the certain things they're optimizing, and then that is where the area, that is where the demand is. What I mean from this session is that this is where the faculties or research scholars should focus on actually, right? So maybe in depth, if you want me to focus in depth in particular topic, yes, definitely I will help, sir, actually further. So basically all these sessions will give a light, it will give a light, throw a light on different topics. And if you definitely need a more detailed support or any detailed explanation on a particular topic, definitely you can reach us. So we have our separate team.
It's not about the detailed explanation. After discussing some session,
Okay,
then
okay, sir.
as a conclusion, these are the important areas where the research thrust has to be given. Like
Okay, okay, sir.
some capacitor size reduction. There is a work going on in capacitor size reduction or the inductor
Yes,
size reduction. There is some researches are going on in this area, or
yes.
some fast charging or onboard charging. Uh,
Okay.
oh, there are some challenges here.
Okay. No,
Like that.
whatever I told in the session, sir, these are all hot work happening in 2020, 2019, actually. Very, very recent work, whatever I shown you in this presentations, actually. So
Yes,
all
sir.
these are actually recent works. So as you mentioned, yes, capacitor, if you look at the inverter side, sizing itself is a very difficult activity, sir, actually. Sizing of the capacitor, right sizing of the capacitor for a certain application, that itself is a area where companies are struggling, you can say. So yes, as you mentioned, yes, even that is also one best area of work. So we can faculties can focus on developing a methodology, a better methodology to size the DC link capacitor or the components present in the EV system, basically related to DC-DC converter or the inverter module. So even that is also having a good scope, actually.
Whether anybody has used ultra capacitor based inverter system or battery charging systems.
No, no, sir, no, sir. That means for the battery application, yes, they will do. But for this particular these kind of applications, right? For this normal inverter application, they will not introduce any ultra capacitors or things.